Okay.
Okay, good afternoon, everyone. Can you see my slides?
Yeah.
Okay, awesome. All right, I would like
Okay, we don't hear you. So some technical problems. We do not see. I don't see your talking. Okay. Oh, try again.
Can you hear me again?
Yeah, we see you, but not your talk.
Okay, I'm going to share again. Somehow I
Okay,
will spell out.
okay, 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 okay.
All
Yes,
right,
yes, we see it.
that's better, right?
Yeah.
Okay, again,
Okay,
I
okay.
would like to thank the organizers of the conference to give me this opportunity to talk about neutron star structure in the era of multi-messenger astronomy. And in this talk, I would be giving some basic introduction about neutron stars and the role of the nuclear physics in the structure of neutron stars and some astrophysical constraints that were recently obtained in light of gravitational waves. Then I'll make some summary and discuss some concluding remarks. So although discovered about 53 years ago by Jocelyn Bell in 1967, neutron stars were first anticipated in the year of 1931 by Lev Davidovich Landau while he was in Zurich, and in his discussions with Bohr, he had come to a conclusion that said that when some heavy stars collapse, the density of matter becomes so great that atomic nuclei might come to a close contact, thus forming a one gigantic nucleus. Of course, at the time, neutrons were not discovered yet. Neutrons were discovered in 1932 by Chadwick, and in 1934, the term neutron stars was coined by Baade and Zwicky. So we can say that neutron stars' first anticipation or prediction were made about 89 years ago. Now, what is the progress since then? First, we discovered in 1967. Today, we know a lot about it, but there are some uncertainties that I would like to talk about. So they are very similar in terms of when you compare nuclei and neutron stars in terms of their densities. For example, the average density of a typical nucleus is about 0.7 nuclear saturation density. And on the other hand, the average density of a typical neutron star could be several times nuclear saturation density, but they are of the same orders of magnitude. Nevertheless, the number of nucleons in a typical nucleus could be in the orders of 10 to the power 2, whereas a neutron star has 57 orders of magnitude more nucleons than a typical nuclei. One is supported by surface tension and the other is supported by gravity, and their sizes also differ by 18 orders of magnitude. Nevertheless, they are both governed by the same physics. So this is the physics of the nuclear strong interaction. That's what at least we think that it is. And that's why we term it as a neutron star. Now, neutron stars are not made only of neutrons. They are made of neutrons, protons, electrons, and muons. They come in a so-called beta equilibrium with one another. On the other hand, a nucleus, a typical nucleus, only has neutrons and protons. And if you take an equation of state to build the structure of a neutron star and the nucleus, you would have to solve either relativistic nuclear structure equations for typical nuclei or a general relativistic stellar structure equations for a typical neutron star. You can see that at the center of the most nuclei, nuclear density saturate. That's why it's known as a saturation density. On the other hand, nuclear densities keep increasing depending on the mass of the neutron star, and they can go several times nuclear saturation density. There is one similarity though. A stiff equation of state and a soft equation of state behave the same way. In other words, a stiff equation of state creates a very large neutron star and also a very large neutron skin, as we say, and a soft equation of state, on the other hand, will give compact neutron stars. So in general, the properties of neutron stars are very complex and fascinating at the same time. I would like to concentrate on the structure of it, not all the details of it. For example, they have a very strong magnetic fields, they rotate very fast, and there are some topological structures in the inner crust known as nuclear pulse. I'll not talk about them. Mostly, I would be concentrating on the structure of neutron stars as referred to the equation of state of dense matter. So the neutron star can be essentially studied into three regions: the inner core and outer core, known as the core, which is made of liquid matter, and the inner crust and the outer crust, which is a solid region made of Coulomb lattice and a very thin atmosphere. So the majority mass of a neutron star comes from the inner core properties, so the equation of state of the inner core. When you take very well constrained nuclear models and predict the mass and versus radius relationships of neutron stars, you will come with this kind of prediction, as was taken by this paper posted here. You can see that whereas these models are very well fine-tuned to nuclear structure observables and nuclear properties, they predict a very large range of neutron star radii. So where does this uncertainty come from is essentially because of our poor knowledge of high density equation of state, as well as the so-called isovector sector of the nuclear interaction that's not very well constrained. Most of the data that we have constrains nuclear equation of state for symmetric nuclear matter, where the number of neutrons and protons are very close to one another. Now, what is actually the nuclear physics input that we need to know? In order to describe the neutron stars, of course, we would like to introduce the so-called nuclear equation of state that I've been mentioning. And there are many nuclear models exist in the literature. Most of them are based either on relativistic or non-relativistic interactions, and which use either realistic or phenomenological potentials. And in general, the pressure of a nuclear matter is related to its energy density through this thermodynamic relationship. In particular, it becomes interesting when you expand the energy per nucleon, or the energy density, as you say, in terms of this so-called isospin asymmetry parameter. It becomes very useful when you apply it to neutron star structure, because the number of neutrons, or the portion of neutrons, fraction of neutrons in neutron stars is greatly larger than the fraction of protons. Now, as a result, when you expand it, the first coefficient of such expansion is referred to as the symmetry energy. Furthermore, you can expand it in terms of saturation density. You can make a Taylor expansions, and these coefficients are usually nice tools to study the dense dependence of the equation of state around saturation. So nuclear physicists use these coefficients alone. In particular, this one is known as the binding energy at saturation. It's known as the compressibility coefficient. And this is the symmetry energy at saturation, and that one is the slope of it, etc. Now, how do we constrain all these coefficients, so to say? Nuclear masses, the available nuclear masses, very well constrain the binding energy at saturation density to about less than 5%. And there are some breathing modes in the nuclei, such as giant monopole resonances, that constrain the value of the nuclear incompressibility at about 10% or less. For example, here are three equation of state models plotted. As you can see, they are almost indistinguishable at about saturation density. The deviation is also very little at high densities. Now, high density component of the equation of state is constrained by heavy ion collision experiments, or maybe by observational data, such as the maximum mass of a neutron star. This patch was obtained by heavy ion collision experiment in 2003. And during the heavy ion collisions, the density of matter greatly exceeds the nuclear saturation, so you can have several times nuclear saturation density. Of course, the maximum observed mass, if you believe general relativity and apply nuclear equation of states, can also constrain the equation of state from above. Now, The part that we don't know is the equation of state of pure neutron matter, which is closely resembling the equation of state of a neutron star matter. While there are some recent theoretical progresses on chiral EFT and quantum Monte Carlo calculations that put tight constraints on the equation of state of pure neutron matter below saturations, at above saturations, these models are not very reliable. Moreover, the models that are fitted purely theoretical, there are no experimental data available. This is due to scarcity of the data for neutron-rich matter that we have in experiments. Therefore, when you do various phenomenological models, you get equation of states of pure neutron matter that at saturation, for example, have great variance in the density dependence. You see a very high slope and a very shallow slope. Now, how do we constrain this equation of states or the properties of neutron stars from astrophysics? And one of the constraints that tells about the equation of state of dense matter and also the properties of neutron star is the maximum mass for pulsar timing and or Shapiro delay. And they give very accurate masses of neutron stars by the observations for many neutron stars in binary systems. As you can see, the error bars are almost zero, except a few of them. In particular, the maximum mass of a neutron star observed to date is about 2.10 stellar mass. Now, the other observation is a joint observation of mass versus radius by using X-ray observations, such as the one by NICER. So X-ray observations use thermal emission of a neutron star surface and then constrain the mass radius relationship for a particular source. For example, here are a bunch of sources that are given, and there is an additional one by NICER that can put tight constraint on the neutron star radii and mass. These are all very well aligned with the current models that are in the literature. The one constraint that I would like to talk about is the tidal polarizability, and this is the main component of this talk. So about 3 years ago, two neutron stars got merged, and as a result, this event gives abundant information on the properties of not only dense matter, but also about electromagnetic observations of these collisions that are known as kilonova. So this single event, for example, generated about 10 Earth mass of gold that tells us about the post-iron elements producing sites in our universe. So in particular, when you have two neutron stars are close in contact before the merger, the gravitational field of one star is so strong that it induces a quadrupole deformation on the other, basically a tidal field. Now, this tidal deformation, of course, is related to external gravitational field of the second one, and the coefficient of that one is known as tidal polarizability, which scales as the fifth power of the radius. Now, neutron star radii are very sensitive to the equation of state, as we showed before, and tidal polarizability would be even more sensitive. In this particular plot, I showed that a stiff equation of state can give you a very large radius, as well as very large tidal polarizability that's calculated in here. Whereas the soft equation of state would give very small one. Now, GW170817 gave in particular information about this tidal polarizability. The information came as such. So the quadrupole deformation, the induced quadrupole deformation, would advance the orbit and change the rotational phase. In particular, in this picture, you see a black hole merger, that there is no quadrupole deformation because they are point-like sources, and you have a gravitational waveform. When you change it to neutron star merger, you see there is advance in the orbit and there is a change in rotational phase. So you can compare them. Now, this change in rotational phase gives information about this tidal polarizability or the value of that quadrupole deformation. The calculations are, of course, extremely complicated if you go near the merger, and it requires numerical relativistic simulations. But before the merger, these calculations can be done in post-Newtonian limit. Now, fluffy stars, which are very sizable, they collide earlier, which means a stiff equation of state model that predicts a neutron star would collide much, much earlier and at lower frequency. On the other hand, the compact stars would continue to orbit and merge at a very high frequency. So there are these differences. In particular, we used the equation of state models from various relativistic mean field models. We chose these mean field models for one particular reason. These are energy density functions that can be applied to both nuclei and neutron stars, but also it can be extended faithfully to the core of neutron stars region, because relativistic mean field models or the relativistic interactions are naturally causal. So they do not violate causality. And with this 10 finely tuned relativistic models, we calculated the properties of tidal polarizabilities of a binary system that was observed from GW0817. Now, this particular band is the 90% confidence level that was obtained by the original publication. And as you can see, many of the equation of state models are easily ruled out, those that are very stiff. But some of the stiff equation of states may already be ruled out by some other analyses that were done that suggested that the maximum mass of a neutron star cannot be more than about 2.17 solar mass. Nevertheless, the equation of states that are ruled in can be then plotted in the terms of mass versus radius relations. And you can see in particular that the radius of 1.4 solar mass neutron star should be something about less than about 14 kilometers. So you can go deeper into the story and try to understand the dense dependence of the symmetry energy, the component of the equation of state, that tells that for those models to agree with the 90% upper bound of the gravitational waves observations of tidal polarizability, this density slope should be smaller than 80 MeV. This is a very interesting constraint. And there are other studies, of course, that study and arrive at the same solution of about less than 14 kilometers. Now, if you go a deep, detailed analysis of Bayesian analysis of this particular data and use the so-called equation of state from empirical local density functionals, then you can study even more detailed correlations between the tidal polarizability and various nuclear property properties, like such as the symmetry, energy density slope, and its second derivative, etc. In particular, you'll find that the tidal polarizability is strongly correlated with the dense slope of the symmetry energy at saturation. But for large stars, this correlation becomes weaker, whereas the correlation remains strong with the pressure at twice nuclear saturation. So the knowledge of pressure at about twice nuclear saturation is very important. Or low mass neutron stars will give more information about dense dependence of the nuclear symmetry energy. There was a very interesting study that was recently in 2019 that came out. It was the gravitational waves from this GW190814. And in particular, they observed that a 23 solar mass black hole got merged with about 2.6 solar mass compact object. The nature of this compact object was not known at the time, and still it is the object of study. In particular, today I just checked that the paper had already been cited by 142 times and is counting. So far, analysis suggests that this compact object could be either a rapidly rotating neutron star or a black hole or a quark star. So in collaboration with my colleagues, we tried to understand the nature of this compact object, and we created a model called the Big Apple, honoring the state of New York and the city of New York, actually. And this is a relativistic energy density functional that very well agrees with the nuclear structure experimental data, as well as it agrees with all astrophysical observations. For example, it goes right through the middle of the point that was predicted by NICER on the radius of a neutron star. So this model in particular gives a 2.6 solar mass neutron star, so everything works very well. The calculated tidal polarizability from this model is about 720, so 717.3 to be exact. This is in agreement with the original analysis made by GW0817, but overestimates the later analysis made by them that suggests that the tidal polarizability should be much smaller. So there is some tension between GW170817. However, this tension does not exist when it is compared with the analysis made by GW190814, where and the analysis of neutron star black hole scenario, they get about 616 plus minus these values. So in many ways, the model looks to be suggesting that this particular source is a neutron star. Nevertheless, when you take it and try to predict the equation of state of symmetric nuclear matter, for our model, we find that the pressure for this model at about 3 to 4 times nuclear saturation density is extremely stiff, meaning that it overestimates the observational data constraint obtained by heavy ion collision experiment. So while this data has a very large error band, the logarithmic plot shows that this is quite going quite higher over the bar. In principle, of course, it's not the equation of state of symmetric nuclear matter that must be obeyed. One could get the equation of state to be very stiff by making the nuclear symmetry energy very stiff. But our models currently are rigid enough that does not allow us to make nuclear symmetry energy to be very stiff. So we come to a conclusion that this companion, if the nuclear symmetry energy is soft, then this companion must be a black hole rather than a neutron star. So I just wanted to summarize what is going on today. So the historical first detection of gravitational waves from this GW170817 had already improved the equation of state of nuclear dense matter. Now, on the other hand, nuclear structure experiments will continue to provide information on the equation of state at and below nuclear saturation. There are some important experiments going on in Jefferson Laboratory and also FRIP, facilities for radioisotope beams in the United States, that aim to measure the properties of neutron-rich nuclei, as well as, for example, neutron skin of heavy nuclei such as lead and calcium. Now, they would give important information on the neutron star structure. On the other hand, the future and current heavy ion collision experiments that would constrain the equation of state at supra saturation density. So these are relevant to the core of neutron stars. And the current and future gravitational wave observations from neutron stars mergers and also neutron star radii observations, such as from NICER, would provide tighter constraints on dense matter equation of state. So there are more exciting opportunities that are ahead of us. And I would like to thank my collaborators who participated in these discussions, Paul Face and other collaborators that had participated in this. And thank you again, the organizers, for giving me this opportunity to talk and for your attention.